Hello, everyone. We are continuing this course of 3 lectures on statistics of eigenvectors of non-Hermitian random matrices. And I will start with summarizing what we basically discussed in the first lecture. So we started with non-normal diagonalizable matrix X and defined the matrix of inner products of left and right eigenvectors, which are also in the literature frequently called the matrix of eigenvector overlaps. And this matrix reflects one of the most profound differences between non-normal and normal matrices, the fact of non-orthogonality of separately in the set of left and right eigenvectors. Diagonal overlaps of, diagonal entries of this matrix, so diagonal overlaps for brevity, we discussed that they are just squared eigenvalue condition numbers which control sensitivity of eigenvalues, ZIs, of this matrix X against additive perturbation of the matrix. Then we consider specifically random non-normal and non-Hermitian matrices, the famous classical ensemble complex Chynadiyovo matrices, which is characterized by joint probability density, Gaussian joint probability density. So every entry is independent and identically distributed normal variable. And just when we integrate that against flat Lebesgue measure, we just get this expression for the joint probability density exponential minus trace of matrix G times its Hermitian conjugate. Then, in order to characterize these diagonal entries of matrix OIJs or OIIs, we followed a suggestion of Choker and Melich and introduced a so-called Choker-Melich diagonal correlator by this expression, expectation of these values or diagonal entries OII weighted with Dirac masses at point Z in the complex plane. The goal is to find expression for explicit expression and eventually study asymptotic behavior of this Choker-Melich correlator when size of the matrix tends to infinity. In order to complete this evaluation, we started with using the so-called partial Schur decomposition for Chynadiyovo matrices. And playing with it after some steps, we were able to show that basically this diagonal Choker-Melich correlator can be expressed as some basically derivative of the determinant of a matrix of size 2n by 2n, matrix M, depending on two parameters. One parameter Z is just position or in the complex plane where we are going to study properties of these eigenvectors. And second, just auxiliary parameter mu, positive real parameter mu, which basically is used to differentiate upon. And after differentiating and setting it to 0, we get quantities of interest. In particular, we get this diagonal correlator, but as a byproduct of those exercises, I also showed that the simplest non-trivial spectral property, namely the mean eigenvalue density, is also related to the same object. It's just expectation of just determinant itself at parameter mu equals 0. So if we evaluate this expectation at non-zero mu, we simultaneously get access to both these quantities. Important to remember that as a result of this partial Schur decomposition, averaging here goes not over the original set of n by n Genebra matrices, but over Genebra matrices of reduced size n minus 1 by n minus 1. But of course, the procedure of evaluating this expectation value for the determinant, I mean, one can do it for any n and then just take the size being n minus 1 in the end. So I will demonstrate it just for brevity in order not to deal with this larger index n minus 1 all the time, which is not convenient. I just demonstrated for n by n matrices. And just to simplify notations. And the technique, there can be various techniques of evaluating this expectations of the determinant, and eventually we will see more complicated objects like products of such determinant. There are various possible approaches, but I think the most efficient one is based on using integrals over anti-commuting or Grassmann variables, for which I expect the audience already to be familiar with, but I will remind it very briefly here what is going on. So we need to evaluate this determinant of 2n by 2n matrices, and for this we introduce two different vectors of size n with n components, and every component of this vector is anti-commuting variable. So one vector I will call phi, and corresponding entries are phi1 to phi n, and its counterpart will be psi with corresponding entries psi1 to psi n. All entries are Grassmann or anti-commuting variables. Within each vector, they anti-commute, as it's written here, phi's between themselves and psi between themselves. They also anti-commute between two different vectors, phi and psi. And also we, for our goals, we need to introduce so-called Grassmann differentials, which are just, in fact, also anti-commuting variables, which anti-commute between themselves and anti-commute with all phi's and psi's. We should remember the so-called Berezin integration rules, first defined by Felix Berezin in mid-60s, which was a great development, very important development. He just noticed that one can introduce integration, which is in fact for these variables is equivalent to differentiation in some sense. But it's still useful to think of it as integration. And rules are very simple. Integrals of every single anti-commuting variable is just 0. And the only non-vanishing object is just psi d psi or phi d phi, where one can choose any convenient normalization. I choose it 1. Then just denoting products of differentials for phi and psi by bold-face differentials, just for brevity. And then finally combining all 4 differentials of these vectors. So in one big differential, one can use the following identity. So basically, we are dealing with block matrix. Each block is n by n matrix. So I just symbolically write it A, B, C, D. And determinant, I mean, the great discovery of Berezin was, or the first probably discovery of Berezin was that if one introduces these rules of integration, then integral of a quadratic form, so analog of Gaussian integral, one can say Gaussian integral over anti-commuting variable, produces just differential of the corresponding matrix defining quadratic form. Here I just need block matrices, therefore I need several copies of these vectors. So I need 2 copies of phi and 2 copies of psi, but this is, one can think of them as just long Grassmann vectors each from the left and from the right. This is the identity, the main identity that will be used. Now I just should use it for particular choice of our block matrices. So I just use the same identity and substitute our matrix here. So this is a matrix. We have this, on diagonal we have simple blocks, just proportional to identity matrix. But off diagonal we have these characteristic matrices for G. Okay, now we need, we start with explicitly writing expression for this quadratic form, just multiplying from the left and from the right this block matrix with psi's and phi's. So what we get? We get, of course, phi 1 psi 1 and phi 2 psi 2. These are terms multiplying with square root of mu. And then we get phi 1 times these blocks times psi 2 and phi 2 times this block psi 1, right? So this we get. This, I just put here everything which does not contain matrix G, but I basically used a simple rewriting, simple but very useful for keeping track of various degrees of freedom or just variables in the short form. Sorry for jumping. It's in fact my screen seems to be very sensitive to when I press on this, it just jumps. I'll try to not to press. But okay, so of course there are terms phi, for example, phi 2 conjugate G psi 1 and phi 1 G psi 2 with i's. But I prefer to write these quadratic forms using trace operation. For this, I need to introduce the matrices A and B, which are tensor products of, made of tensor products of vectors psi and phi, psi 2 with phi 1 and psi 1 with phi 2. And then using obvious identity that trace of a matrix times such a tensor product is just equal to quadratic form, I will write it in this form. So why I prefer to go this way? Because in this way, it's immediate to average over Gaussian distribution of entries of G. Of course, to average over Gaussian distribution exponential, we know it's always simple, but if without this notation, it will be a little bit long expression to write. And here it will be extremely concise because of the following identity, which you can easily check, is just a Gaussian identity, a Gaussian integral identity, that exponential of minus, trace G times some matrix plus conjugate G times another matrix is just, the result is exponential minus trace of A times B. So it's very nice identity, Gaussian identity. So the only thing we need to calculate trace of A times B here, and it's immediate because of rank 1 structure of this tensor product as a matrices. It's very easy to calculate trace of their product. It's basically immediately we see that this is this product of two scalar products, phi 1 is psi 1 and phi 2 is psi 2. So in this way, we basically performed this ensemble average in the most efficient and economic way. So this is the result. So just summarizing, we arrived to expected value of our determinant of interest in terms of an integral over 2.
I'm sorry, can you show the previous slide for a moment?
Back? This one?
Yes, yes.
Questions, please? I do not hear any questions.
Thank you, thank you. No, no, I just I'm right. Thank you. Go.
Okay.
Yeah.
Okay. Yes, do not hesitate to slow me down if you feel that something is either unclear or I try to be pedagogic in these lectures, but still I maybe jump over something. So you may slow me down. Okay. So we arrived to this expression. We expressed our expectation of interest in terms of integral over 4 vectors and vectors containing Grassmann variables. But we see that basically the result depends on these vectors only in terms of various scalar products. And I won't use this way. This gives one way of evaluating this integral, so-called, I just mentioned it, but I won't go this way, so-called super-Bosnianization trick, which was suggested by basically Martin Zirnbauer. And some people prefer this trick, but I will deal with this integral differently. I think it's easier to deal with this integral in alternative way. I will use so-called Hubbard-Stratonovich identity, and this is, this identity, for those who maybe not heard about it, is nothing else as just a Gaussian integral but read from left to right rather than from right to left. So it's not, it's still integral equal to something, a Gaussian integral, but it's used in opposite direction. So what is this identity? There are various versions of this identity, but here, so what is the idea? Idea is that before averaging, this integral was Gaussian integral with respect to Grassmann variables. Now we have quartic term in Grassmann variables, which is inconvenient for evaluating this and hinders our progress. So let us linearize it back, but not, of course, back in the sense of averaging over matrix, but rather by just introducing auxiliary Gaussian integration over just pair of complex, basically over complex variable q, auxiliary variable, and just Gaussian integral q bar q minus q times something minus q bar times something. It gives exactly this. It's easy to check. It's Gaussian integral. Gives back exponential of the product of this. Let me remind you that scalar products of Grassmann variables, they are commuting variables. So you can, from the point of view of algebra, you can deal with them as they were normal variables. So this identity is valid also. The only difference is that these combinations are so-called nilpotent commuting variables. It means that some high power of this object will be zero eventually, but otherwise algebraically it's just commuting object. So we can use our standard tools. Okay, so how it helps? Now, instead of this exponential, we substitute back to this integral, now this integral representation, and change the order. We now take outside integration over q's, and we see that in the integral, now with respect to Grassmann vectors containing Grassmann variables, again becomes in exponential bilinear in Grassmanns. Therefore, it's just basically can be written down as standard Gaussian integral. And we know that Gaussian integrals over Grassmann variables produce determinants. So you won't be surprised to see that we immediately can perform this integral over psi's in no time and get just determinant of the corresponding quadratic form. It's written now here. We see that it's still, of course, matrix of size 2n by 2n, but it's much simpler. As a result of averaging, it's a matrix where every block is proportional to just identity matrix of size n. And therefore, determinant of such matrix is trivial to calculate. It will be just determinant of the corresponding 2 by 2 matrix raised to power n. And therefore, determinant of this 2 by 2 matrix is immediate to calculate, and this is the result. So we now represented our object of interest as just integral over a pair of complex variables. This is, of course, a huge advantage. Okay, one can even proceed to large n analysis directly here, but there is, in fact, it's useful to make one more step, namely here to pass to polar coordinates for this pair of complex variables. And remember the definition of Legendre polynomial. Okay, here, small misprint. Of course, this small case n should be just equal to this. So it should be capital N, P capital N, with index n, integer n. This is standard definition of Legendre polynomial. And if we go to polar coordinates, we notice that we have this, it's easy to see, we will have this expression. And therefore, after simple manipulation, we just arrived to one-fold real valued integral over positive semi-axis of variables r's of some pre-exponential terms raised to power n over 2, then exponential minus r, just inherited from this term, the exponential of minus q bar, and then Legendre polynomial of size n of this object. Okay, now this already nice expression, and the first thing to do with it, to use it, is just to get explicit expression for the mean eigenvalue density. So I just formulated it as a proposition that from this immediately follows that eigenvalue density is just proportional to the so-called incomplete gamma function of two variables n, which is size, and modulus z squared, where z is a position of the complex plane. And for those who do not remember or never encountered incomplete gamma function, this is just definition of incomplete gamma function. Now, proof of this proposition is very simple. We had this expression in terms of expectation of this basically object, where we set mu equals 0, and if one sets mu equals 0 here, one gets this unpleasant argument becomes just 1, right? Because here we have r plus modulus z squared, and here we have the same square root of the basically, so the same expression. So it just becomes 1 in this limit. Here it's also a huge simplification, becomes r plus z squared squared. And then by simple shift of, introducing r plus modulus of z squared as new variable, one sees that due to this fact, exponential minus z squared will be cancelled, and we get just gamma function by definition. So this result is valid for arbitrary n. So I think this is probably the simplest and the most straightforward way of deriving this quite famous and eventually simple expression for the mean eigenvalue density of Geneva ensemble. There are, of course, zillions of alternative ways, but I think that this method may be the simplest one to derive it explicitly. And now what remains is, in the last bit, I forgot to mention that Legendre polynomials at argument 1 is just 1, and so this just goes away. Okay, now let us now study what happens when n tends to infinity. And then probably, or you may remember discussion in the first lecture that basically eigenvalues, support of eventually limiting support of eigenvalue density for Geneva ensemble for large n is a disk of radius square root of n. So it makes sense to scale that variable as w times square root of n. And indeed, if we apply this scaling, then one notices that, it should, again, its misprint should be no this equality here, just limiting value of this ratio is 1 if modulus of w is smaller than 1, and 0 if modulus of w is larger than 1. When considering this limit, I assume that w is fixed variable. So this I call characteristic function of the disk. Now, how to prove it is just straightforward application of Laplace method of asymptotic evaluation of this integral, right? So one just first changes u to n times u, nu u, and then just evaluates this integral by its stationary point, right, by saddle point. So it's very simple evaluation, and this you get as a result. Okay, so we already have something. We have the density, although it was not our goal, but I think it's a nice calculation. But in fact, now we need, in order to get our main object of interest, diagonal Choker-Melech correlator, one needs to differentiate this over mu, and after that, set mu to 0. This is slightly more involved. It's not first you need to differentiate these expressions, but it's clear that it's also not that difficult exercise. So we all, after differentiation, one should remember that not only Legendre polynomial at argument 1 is 1, but its derivative at 1 is also a simple number, just n times n minus 1 divided by 2. And in this way, after just diligently performing differentiation, and one finds this explicit expression as a one-fold integral over R. We see it's also not very difficult. And using definition of incomplete gamma function, one gets explicit expression for any n for this diagonal Choker-Melech correlator. Again, in order to get it's asymptotic, we rescale z, use asymptotic for gamma function, and derive to the announced result that in order to get a finite limit for this object O, one needs to not only to rescale, but also divide by n, which shows that it's typically of order of n. And then this is the result that I announced, that it's non-zero inside the unit disk and depends. It's not constant like density, but it's simple expression 1 minus double modulus of w squared. Okay, so we completed this task. Again, I believe this is the simplest possible derivation of this result, although there exist alternative derivations. Choker-Melech and some other people have their alternative derivations, but to my taste, it's the simplest one. Okay, in fact, in the original paper of 99 of Choker and Melech, they not only provided this value for this correlator that we just evaluated, but they also conjectured that if one considers these diagonal entries of the matrix of overlaps as random variables, then these random variables they are heavy-tailed. It means that their probability density must have a tail, cubic decay tail. So not only power law, but also particular, they even conjecture that it's cubic decay. They had some imprecise argument why. They were also able, in fact, they performed explicitly calculation for 2x2 matrices. Of course, for 2x2, you can do whatever you wish. And they obtained this tail, but also numerically, they seen that it's valid for arbitrary n. And for about 20 years, this remained open. And then Paul Bourgaard and Guillaume Dubache managed, realized that in principle, how in principle and in practice, to find this probability density in the limit of large n, when n tends to infinity. And they got explicit expression for it. And immediately after that, I found the alternative way, which I'm going to discuss with you, very different from their proposal, which not only reproduced this result for complex G-Neighbor, but also allowed to get its analog for real eigenvalues of real G-Neighbor matrices. So let me remind you that we discussed in our first lecture that real G-Neighbor matrices, they have of order of square root of n eigenvalues on exactly on the real axis. Those enjoy different statistics from eigenvalues in the complex plane. This method that I'm going to discuss can be applied to both situations. Method of Bourgaard and Dubac, it seems, at least at the moment, seems only to be applicable to complex G-Neighbor case. But I think that it also probably can be developed further to cover both cases. Now I formulate results for both cases as the following theorem, namely, let us introduce the probability density of a variable, which a natural variable, and we know that these diagonal entries, they are of order n, and also that for normal matrices they are 1. So let us consider this natural object, or we subtract 1 and divide by n. So we expect, we may expect, and indeed it's the case, that this is a correct scaling variable in the large n limit. So this is basically scaled, if you wish, diagonal overlap factor. And then if we are interested in the probability density for those eigenvalues which are in the vicinity of the point z in the complex plane, then they exist corresponding. One can show that the corresponding limiting probability density exists infinite inside this G-Neighbor disk, and explicitly given by the following expression. It has a tail which is cubic for complex G-Neighbor, and quadratic, so decays even slower for real eigenvalues of real G-Neighbor. So in order to treat both cases simultaneously, as it's conventional in random matrix literature, I introduce parameter beta 1 for real case and beta 2 for complex case. This is so-called, conventionally, it's called Dyson symmetry parameter. In terms of this, this parameter, one can explicitly write this probability density. It has exponential minus up to normalization 1 divided by t, and this object O1 beta of W, it's not, in fact, it's just the object that we already seen when discussing mean value of Choker-Melech correlator. This was exactly it in the case beta equal 2. So we see that the mean sets the scale for fluctuations of this t, but otherwise it's cubic. T here and t to power 2 here, all in denominator, so 1 over cube. So if the tail is 1 over cube, then the mean exists, but higher positive integer moments diverge. So the Choker-Melech correlator, in fact, is the only integer moment which is finite for beta equal 2, but for beta equal 1, even mean does not exist. It's just typical value, because for tail decaying as 1 over t squared, mean will be logarithmically divergent. That's probably why Choker and Melech did not calculate for beta equal 1 this expectation, because it just does not exist. But as a distribution, it's well defined. Now, in the remaining part of this lecture, I will show you how to arrive to this expression, and in fact, for even more, how to arrive to expression for any finite n, but not in full generality. So I won't derive this full generality expression. I only derive it for a special point where computations are simpler, significantly technically simpler, although conceptually they are the same. Namely, the center of Genibor disk, the origin, z equal 1 or 0, or w equals 0. For this, I will show you the derivation in full. Okay, so I sketched the proof, main steps of the proof of this theorem. I sketched it for complex Genibor ensemble. For real Genibor, it's somewhat more involved, but ideas are similar. Okay, now let us try to do this computation. I come back to expression that we already seen in the first lecture, that this object, diagonal entry of matrix of overlaps, is just equal to 1, so it's natural to subtract 1 anyway. And this will be our random variable t now. And it's given by quadratic form built on inverse of matrix B, made of this product of characteristic matrices for Genibor matrices of size n-1, and W's are, as we already discussed and seen in previous lecture, very importantly, they are IID complex variables. So at the first step, so the idea is, let us introduce for this object, which is variable t, introduce just characteristic function, which is nothing else as just Laplace corresponding Laplace transform of the probability density for this random variable. So explicitly, we just take exponential minus p, Laplace parameter, this random variable, and we, of course, condition it for eigenvalues in the vicinity of a given point on the complex plane. And we need to average over everything, over all these variables. Z1, or Z1 is trivial averaging because of delta function. W, also simple because it's Gaussian vector. and the most non-trivial part about or average over these Genibor matrices of size n-1. Now, explicitly, we do, I just write it here. Again, averaging over Z1 just gives us this factor exponential minus Z squared. We already seen it. Averaging over Gaussian averaging over W. This is again Gaussian integral, right? Because it's just again quadratic form in W's, so we can easily perform it. Will be determinant of the corresponding quadratic form, identity matrix minus this, and we arrive. The only non-trivial part remaining is to perform averaging over these matrices G1, which I symbolically write again in these brackets. We see that one needs to evaluate basically after doing these computations and making simple algebra, playing with a little bit trivially with this determinant which arise as a result of integration. So as a result of Gaussian integration, we get 1 over determinant. This is standard Gaussian integration, not Grassmann, when we get just determinant, but standard complex integral. And therefore, we basically, after playing with that, we get the following expression. The object of interest now, not dissimilar, but more complicated, just so somewhat more complicated than one which we encountered in our calculation of just first moment of this distribution. For first moment, we just need to average basically this type of determinant also with diagonal, basically with non-vanishing diagonal. Here we need to average first of all squared, this determinant squared, but also divided by similar object with non-vanishing diagonal. And we need to organize this computation. And for this, we now use the method which is known as supersymmetry approach, or I mean, in literature frequently abbreviated as SUSY approach, supersymmetry approach. So supersymmetry is basically the idea of combining for computations of both Gaussian integrals over Grassmann anti-commuting variables and over commuting variables. And this is exactly what we will do here. So we start with what we already seen. And now you see that I suppressed Z here. So now instead of Z or minus I times Z minus, I have just G. This will make my life slightly simpler technically later on, and also expressions are not as cumbersome as they appear when Z is retained, but conceptually all the steps are the same for with or without Z. So first step is as before, representing still jumps, representing determinants as integrals over just a single determinant as integral over these sets of phi's and psi's, 4 vectors phi's and psi's. And then also we need to consider, we remember in our previous expression, we need to represent squared determinant. So it's product of 2 such integrals. So we need one more index, which I will call it sigma, which will take values 1 and 2 just to represent each product of 2 determinants. It's just doubling the number of variables, nothing more. And again, I can squared can be conveniently represented as trace of G times some matrices. But now these matrices will be sums of these tensor products, which makes them higher rank. And therefore, we may expect that it will be more involved objects appearing after averaging. Now, simultaneously, we represent the determinant in denominator as, again, as Gaussian integral. In fact, here some of you may wonder why we do it, because we obtained this integral in the denominator. We arrived to it in our derivation just after performing integration over W's, which was Gaussian integral. Okay, in this particular example, it's indeed the case. One can introduce these determinants in on earlier stage by some convenient integral transformation, but it's, in fact, this way is more transparent, and also what is important, can be generalized to other quantities of interest. We will do it, maybe some of these generalizations tomorrow in our last lecture. But here I just represent general steps of this supersymmetry approach to this problem. So we represent determinants as Gaussian integral over a pair of complex vectors S1 and S2. And again, I explicitly rewrite it as trace of G times these tensor products. Now I take this integral over commuting variables and these two integrals over sets of anti-commuting variables and represent them as one long integral. And now really this notation of traces is very handy because it allows to write things relatively compact way. Otherwise, it will be not easy to represent on one slide. So this is now what we get. We need now to perform this bracket stand. I remind you, averaging over Genebra matrices. Here again, for brevity, I use Genebra matrix of size n rather than n-1. But in the end, I will just set n to from n to n-1. It's trivial change. So I do it for n by n matrices. And when combining all these integrals, we of course have products of all differentials. This is trivial. But we also nicely have these matrices, which I call A tilde and B tilde, which are made of sums of tensor products of all involved combinations of here of Grassmann vectors and here of usual complex vectors. And therefore, we can apply now the same identity as we did last time. Trace the result of this, performing this averaging over Genebra, it just amounts to calculating trace of matrix A times matrix B. Okay, maybe they are not most simply looking matrices, but after all these terms in the sum are just rank 1, each of them rank 1 matrix. So it's, in some sense, it's rank 3 matrix. So it's not a big rank. So it's relatively easy to calculate trace of product of this. And one may notice that convenient and expedient way of representing this result this trace is the following. First, okay, it's just product, it's trace of product of this part with this part, not involving Grassmann variables. This is just this combination. This is, very straightforward. Now, will be trace of product of this with product of Grassmann from on the right or in B. This can be represented after doing this trace, can be represented as trace of product of two 2x2 matrices. And these 2x2 matrices, they are matrices made of all possible scalar products of Grassmann vectors phi and psi.
We have sorry, we have one question, so let's go.
Yeah. Could you please explain how we obtain a product of S1 star S1 and S2 star S1?
Okay,
yes.
You see, or let us do it. You see, first of all, trace of S2 tensor S1 star S1. S1 star S1 is just a scalar, so it can be taken out immediately. It's S1 star S1 will be out, and it will be trace of S2 tensor S2. But tensor of, trace of rank 1 matrix S2 tensor S2 is just this. It has only one eigenvalue equal to this scalar product. So here the trick is that trace of tensor of a vector with itself, vector tensor with itself is rank 1 matrix. Rank 1 matrix has single eigenvalue, non-zero. All others eigenvalue are zero by definition of rank 1 matrix. And this eigenvalue is nothing else as just a scalar square of this vector, of which we make our matrix, right? This is standard fact. Okay. So trace will be just equal to this scalar square. Is it clear now?
Yes, thank you.
Okay. In fact, all the rest is just the same, but just diligently considering each of these products doing the same procedure. So basically, this term is just representative of all other terms. Now, it's just convenient to notice that this part, which one obtains by considering traces of these combinations with this combination, can be represented as trace of product of 2 by 2 matrices, Q with index 1 and Q with index 2, which are made of all possible products of Grassmann vectors phi with only Grassmann with Grassmann vectors psi. So we just introduce this is we will see why it's convenient to write it in this form. And also there are terms which one obtains when one takes, for example, we need to consider trace of AB. One takes trace of this times, for example, one of terms here. One gets then by combinations which will be containing 2 Grassmann vectors and 2 usual vectors, and this will be again by this rank 1 property will be just simply scalar products of corresponding vectors. It's just that they are, each of these scalar products is linear in Grassmann. So we see that there exist terms in some sense can be classified by the number of Grassmann variables in them. Here there is no Grassmann variables. Here all combinations are quartic in Grassmann variables. And here all combinations are bilinear in Grassmann variables. And so we performed this average, but now in the next step, we'd like to do the same as we did when we, in our previous exercise, when we considered this only this simplest Choker-Melech correlator. If you remember, the idea was that we used some Hubbard-Stratanovich transformation to decouple terms which are quartic, which are like here of this type, although they were much simpler form, but morally they were like terms here. We decouple them, and after that, integration over Grassmann variables is trivial because it's just Gaussian and produces determinant of corresponding matrix which is used to build quadratic form. We will use exactly the same strategy here. The only difference is that now we have exponential minus trace of product of 2 by 2 matrices rather than exponential of just product of just two commuting variables. Okay, but there is natural generalization. This is a matrix Hubbard-Stratanovich transformation. It looks exactly like its simplest non-matrix version. You remember, before we had exponential of product of 2 commuting variables was Gaussian integral, and here we had just variable times first in this product plus its conjugate times second in the product. It's exactly the same here, just trace appears. And it's nothing else as straightforward Gaussian integral. So, of course, it's much easier to evaluate it from right to left, but use it from left to right. So it's nothing else as component-wise. If you write it, it's standard Gaussian integral, nothing more, nothing less. But integration now goes over general complex 2 by 2 matrix Q. And now we take this, substitute back to our integral, change the order. So now external integration over Q will be external and can perform Gaussian integral over Grassmann variables very straightforwardly. And this is what we get as a result of Grassmann integration. We get determinant of the corresponding matrices. Now, what are these blocks? Each of these blocks is 2n by 2n. So this size of this matrix is 4n by 4n. Each of these blocks is 2n by 2n. And how are they done? This is basically matrix Q. So this matrix. So what is written here in simple terms? It's just Q11 times identity matrix, Q12 times identity matrix. So each entry of this is just multiplied with identity matrix. So in brief, I mean, in concise form, I write it as just direct product of matrix Q with Yn. Now, this block, it's also, of course, of size 2n by 2n, but it's made of rank 1 matrices of form, basically, when one tensors vector S1 with vector S2 with conjugate vector S2, and then tensors it further with identity matrix of size 2. So these blocks, in fact, are not diagonal. These, I mean, these blocks are each proportional to identity matrix, but here they are not. They are rank, but they are relatively simple. They are rank 1 blocks. So altogether, next step is to somehow evaluate or simplify this determinant. But because of this particular form, one can use the following chain of identities. I leave it to you to verify, but it's really very simple. First of all, using standard, if we have partition matrices, there is standard, I think it's called Schur identity, but anyway, very well-known identity, how to calculate determinants of matrices partition in 4 blocks. And applying it, one gets, first reduces this determinant to determinant of now of 2n by 2n. This was 4n by 4n. Now it's one reduces it to 2n by 2n, but it's of particular form. And due to this particular form, if you write it just explicitly for, I don't know, for say for n equal to, you will immediately see that it's in fact it's product of determinants of such a of 2 by 2 matrices, where matrices are Q times Q conjugate minus eigenvalues of this matrix B star, whatever they are. But B is this matrix, B, right? If we compare, this is rank 1 matrix. So basically it's very, if we consider B conjugate, it's proportional to rank 1 matrix. And it's again has only one eigenvalue. Eigenvalue is just this. So we arrive to much simplified form of this integrand. First, it looks, at least for an experienced eye, looks quite horrible. But if you think of it and play this game, you see that you reduced it to very simple form. Namely, one gets determinant of QQ star to n minus 1. This is because, okay, it's already clear here. It's product of n determinants of 2 by 2 matrices, but only one eigenvalue is non-zero. So if B is 0, it will be just determinant to power n minus 1, and the only one will be not in this product, and the only one non-trivial will be here. It's here. Okay, so now the problem amounts to analyzing these integrals. So it's now we have two integrals, external integrals over matrices S1 and S2, note that S1 and S2 enter only in the integrand in very invariant fashion via their scalar products. And this will allow huge simplification. And also we have this integral over 2 by 2 matrices Q. So in order to analyze this integral, we use the following procedure. First, we use huge invariance of integral with respect to S's. We just introduce, so how one deals with integrals, we depend only on scalar product. One, of course, introduces just polar coordinates, right? So for each of these S, we introduce basically its length as a variable and unit vector, which parameterizes it, its rotation. So the corresponding measures are just standard measures in polar coordinates in n-dimensional space, where d mu's are just a uniform measure for a vector going on corresponding sphere. Now, in order to deal with Q, we also notice that, in fact, Q enters in the form, not, in fact, you see, enters in the form, one can say, somewhat inherited from original form of Genibor matrices, although now matrices which enter this game are 2 by 2 only, which of course huge simplification. They are not n by n any longer. And but the shape is you have only dependence on trace of Q conjugate and also determinant of this form. So it's natural to use just so-called singular value decomposition. So every general complex matrix can be brought to a diagonal form by 2 unitary matrices, multiplying it from left and from right. So what stands on the diagonal is known as singular values, and what stands in these unitary rotations are known as matrices of singular vectors. Okay, so this is again a choice of coordinate, if you like. Originally, we integrate over matrices Q over here. Lebesgue measure is just measure independently in each degree of freedom in each entry of this matrix Q. But in this transformation, of course, we just change variables, change coordinates. We choose useful coordinates, but this transformation is nonlinear, so we need to calculate corresponding Jacobian. Fortunately, it's only 2 by 2 matrices, so it's not as horrible calculation as I showed for this for partial Schur decomposition. It's simpler, but anyway, it's need to be done. It's not one line, but the outcome is that up to factor, I systematically for brevity of presentation do not include constant factors. They can be calculated. So basically, Lebesgue measure is in these new coordinates is proportional, of course, to each differential in this in all R1, R2, and basically Haar measure on the corresponding U2 groups of these unitary matrices, but also has this characteristic structure, which frequently appears, almost always appears when one comes to, when one uses similar parameterization for matrices. This is so-called squared Vandermonde determinant of the corresponding singular values. Sorry. So, okay. After all these manipulations, if you substitute this, you can you see that many degrees of freedom just do not enter this integrand and can be simply integrated out. And what remains now, we reduce this integral to 2 variables, P1 and P2, which are just basically lengths of these vectors S's, so in polar coordinates, and to integration only over R1 and R2. And the integrand is relatively benign. Moreover, it's easy to see that these integrations, if one just expands here all this product of all these brackets, it's very easy. Integrals over R1 and R2 decouple, and each of them gives something which resembles basic, or not resembles, but equal to some combination of similar to incomplete gamma function, in fact. So no, even sorry, maybe here is let me just see. No, it's even simpler here. Here it's not incomplete gamma function, but just simple exponential integral can which here it's simpler, which can be performed explicitly. Just will give you some factorials. So just integral exponential minus r times r to some power. So these are just standard factorials. Here it's simpler. It's not incomplete gamma. Now I can tell you where that if one kept general z, position z in the complex plane, not using this special point in the center of Genibor disk, then one would get a bunch, unpleasant bunch of incomplete gamma functions, which will require some effort in analysis. Here, it's much simpler. All gamma functions just become complete and therefore factorials. Okay, so we integrated out completely this R1 and R2. And now we have integrals which, okay, one should think how to deal with them. They're not completely trivial. They're not like what we've seen over R's, because we have this, in exponential, we have this P1, P2, and integral, which is important, goes over the first quadrant of P1, P2 plane. And then there is a trick that if integral depends on sum and product of variables, it's known that it should be done in so-called, I think it's called hyperbolic coordinates. I'm not sure what is appropriate name, but basically instead of going, if integral depends on something invariant with respect to rotation, we use polar coordinates. Here it's different type of symmetry, but related. So it's so-called hyperbolic coordinates. One basically introduces P1 as some variable times not imaginary exponential like it would be for polar, but exponential of theta, and here exponential of minus theta, where t is positive and theta goes from minus to plus infinity. And then this volume element is just d theta dt. And then after using this, one notice that integral here, instead of P1 plus P1, P2 becomes simple, of course. P1, P2, this is the idea of hyperbolic transformation, becomes just T. But here it becomes integral P1 plus P2 becomes a hyperbolic cosh. So integral of this sort is just so-called McDonald function. It's a very well-known function. And as a result, one gets, for finite n, one gets expression for the object of interest as just combination of these Bessel functions. And then one notices, so what remains is integration over variable t. And one may think that this is nuisance, but it's not, because after changing, in fact, after simple change of variables, one notices that this integral can be represented in the form of Laplace transform. But we remember that our object of interest, I don't know if you remember or not, it was already some time ago, that the object that we wanted to calculate was Laplace transform of some probability density of interest. Therefore, if the result in the end is in form of Laplace transform, we can very easily invert this transformation. So inverting it, we get explicit expression, which is very simple. Basically, this is explicit up to a constant which is known and can be restored from normalization. This is the probability density of this overlap for any value of n. And you see that its tail for large T is exactly 1 over cube, always. But of course, one can further do limit n to infinity, rescaling T correspondingly, and then one gets this result, which I quoted for beta equal 2 in this theorem. So this finishes the material for today's lecture. Thank you.